We know that a charge that's moving through an area of space that has a magnetic field experiences a force that's caused by that magnetic field. The direction on that, of course, is is perpendicular to the velocity vector and to the magnetic field direction, the magnetic field vector. But what if we have charge not just moving as one big bundle, one single charged object? What if we have a bunch of charges moving through an area over some period of time? That's what happens in a wire. We have current flowing through a wire. That's lots and lots of little charges that move through this wire over time. Now, they're moving. They're charges that are moving. They're moving through a magnetic field, so they should experience some force in some direction. But what direction and what amount of force would they experience? Well, our equations up until this point don't allow us to calculate this because we'd have to know the amount of charge. But there's lots of little charges going by all at once. So, which one do we pick? How many of them do we count? And the speed, we don't really have a good way to measure the speed of the charges as they're traveling through the wire. So this form of the equation doesn't really work for us. But if we rewrite this, so I'm just going to drop the absolute value, really the magnitude and the vector signs, and write this as black here. Write this as F equals QVB sine theta, which is how it's written on the equation sheet for AP Physics. Remember, velocity sometimes gets written as, instead of velocity, we could calculate that rather, as the distance traveled divided by the amount of time it takes to travel that distance. So if I've got some length of a wire in here, and we'll call that just a length L, then the speed that those charges are traveling through is the length of that wire divided by the amount of time it takes them to go from one place to another in that wire. And then that's times B times sine of theta. Now, if I rearrange this a little bit and write this as Q over T times L times B times sine theta, charge over time, that should be familiar to us. That's the definition for current. So the force is equal to the current times the length of wire times the magnitude of the magnetic field times the sine of the angle. And the angle we're talking about there is still the angle between the velocity vector and the magnetic field vectors. So in this case, our positive charges are moving to the right. The magnetic field is pointing upward. There'd be 90 degrees between those two. So let's try an example with this. We'll calculate the force that's experienced by this wire caused by this magnetic field when we have current flowing through the wire as shown. So our force, the magnitude of that force is equal to, in the AP Physics equation sheet, that equation is written out like this. Bil sine theta, B-I-L sine theta. So our force here is going to be 500 microteslas, or 500 times 10 to the negative 6th teslas, times our current, 4.0 amps, times the length is 0.5 meters, times the sine of, well, let's see, the velocity vector. The positive charges are moving upward, and then that magnetic field that's pointing into the page or into the screen. So that's another 90-degree angle there. And so the magnitude of this force is going to be, let's see, 500 times 4 times 0.5 is just times 2. So that'd be 1,000 times 10 to the negative 6 teslas. Sorry, not teslas, but that's newtons. Times 1 is just 1,000 times 10 to the negative 6. Or 1 times 10 to the negative, let's see, 1, 2, 3. So 1 times 10 to the negative third newtons. Now how about the direction here? Well, we follow that right-hand rule again. So I, the direction of I, shows the direction that positive charges flow in this this current. Even though we know it's really the negative charges that do the moving, and they're moving in the opposite direction, the math works out the same way if we just think of this as being the direction of positive charge movement. So your pointer finger goes upward on the screen, or toward the top of the screen, or toward the top of the page here. Your middle finger needs to point into the screen. So you're going to have your hand and, let's see, pointer finger needs to point upward. And then your middle finger is pointing into the screen. So that'll be kind of, oops, an extra finger there, kind of in this orientation. And so your thumb is going to point off to the side like this. And again, your middle finger is pointing into the screen there. So this force is going to be to the left. So 1 times 10 to the negative third newtons to the left is the force experienced by this wire.